Hello everyone and welcome. I am Faiza Rahimi and would like to give you a short presentation over my digital poster with the title Helmet RF-applicator for enhancing focal RF power deposition in thermal magnetic resonance of the brain at 7 Tesla. I have nothing to declare. Thermal magnetic resonance uses an RF applicator to add a thermal intervention dimension to a diagnostic imaging device. MRI is a mainstay of diagnosis, but adding a thermal intervention dimension is conceptionally appealing for localized thermotherapy as an adjuvant to cancer, chemo, and radiotherapy. Hyperthermia, by increasing drug delivery, shows excellent clinical results with 15% increase in response. Any in vivo hyperthermia modality strongly benefits from diagnostic guidance, temperature dosimetry, and therapy outcome monitoring facilitated by non-invasive imaging and temperature mapping. Optimizing the performance of RF-applicator configurations can eventually improve the performance of ThermalMR. ThermalMR exploits localized radiofrequency power deposition in a target volume by adjusting the electric field components of multiple independent RF sources. As you see the relationship between the electric field SAR and temperature, this is done by setting the individual electric fields to constructively superimpose in the target volume while canceling each other outside the target volume to preserve healthy tissues. By considering how increasing the static magnetic field strength affects Larmor frequency and electromagnetic wavelength, ultra-high field MRI is an excellent fit for ThermalMR as it operates in shorter wavelengths than conventional MRI, which can provide better localized temperature manipulation along with diagnostic imaging. In this work, two RF array configurations, both with 10 channels, are compared: a 10-channel transmit array using a symmetrical annular arrangement and a helmet configuration, as it is shown, each assembled from 10 broadband self-grounded bow-tie antenna building blocks. SAR calculations were averaged over 10 grams of tissue and phantom material, and constructive E-field interference in the target volume was achieved with a focusing method inside the target volume between 40 to 80 watt per kilogram. Electromagnetic field simulations were performed in CSE Microwave Studio at 297.2 MHz by considering a cubic target volume without any tumor in 4 locations in the brain and by moving it to more than 700 target volumes in the brain with 7 mm step size. To mimic a realistic clinical scenario, a voxel model was generated from a CT head scan of a patient with an intracranial glioblastoma multiforme using Sim4Life. Electromagnetic field simulation results of both RF applicators were performed using a phantom mimicking the properties of brain tissues and the head of the human voxel model Duke at 2 different frequencies. SAR 10-gram distribution shows that the helmet configuration had greater maximum SAR in the center of the phantom compared to the annular array. In both RF applicators, and in both phantom and head voxel model simulations, a better focal point quality is obtained of the helmet than the annular array due to superior coverage of the human tissue and also phantom, and it is higher in higher frequency. SAR 10-gram distributions for 4 target volumes in the brain is shown. The mean target SAR values, MTS, from the helmet array were superior to those from the annular array, as it is obvious. The performance advantage of the helmet array over the annular array is highlighted by the radar plot showing MTS, maximum SAR in target volume, in healthy volume, and their ratio normalized values. To have a better conclusion of the performance of RF applicators, statistical results from more than 700 target volumes sampled in the brain are compared. By moving target as it is shown, higher maximum and mean SAR in the target volume for the helmet array versus the annular array are illustrated into the box plots. Temperature distribution maps obtained for a realistic target volume model from a patient with glioblastoma multiforme show that the helmet array resulted in a higher mean temperature than the annular array for the same total input power. The helmet array showed superior temperature performance than the annular array by comparing accumulative temperature histograms inside the tumor. As a conclusion in this work, We saw requirements of a single multi-purpose RF applicator for ThermalMR and how is it challenging for ThermalMR of the head due to the small surface area around it. And the helmet RF applicator takes advantage of extra area above the head. And two perpendicular self-grounded bow ties improve target hitting and B1 plus uniformity, as you can see in poster 166. This study demonstrates that the helmet RF applicator facilitates a 10% improvement of maximum SAR in the target volume versus the annular array with enhanced target coverage. And our numerical simulations provide a technical foundation for implementation of the helmet RF array configuration and offers a springboard for ThermalMR-based therapy of brain tumors. At the end, worth mentioning that helmet RF applicator enhances focal RF power deposition in the thermal magnetic resonance of the brain at 7 Tesla.